All right, so today we're putting on our detective hats to crack a case that's 300 million years in the making. Our mission? To decode the chemical secrets of a star cluster and maybe, just maybe, figure out how astronomers are using these clues to map the history of our entire galaxy.
So let's just start with the biggest question right off the bat. How on earth do you investigate something you can never, ever visit? Something you can't touch or take a sample of? How do you piece together the life story of a star that's been burning for millions of years from thousands of light years away? I mean, it sounds completely impossible, right? Well, for astronomers, it's all in a day's work.
Okay, let's dive in. Every good detective story needs a crime scene, or in our case, a birthplace. And for our star detectives, the perfect location is something called an open cluster. This is where the story begins.
So, what is an open cluster? Well, the easiest way to think about it is like a giant cosmic family. All the stars inside one are basically siblings. They were all born around the same time from the very same enormous cloud of gas and dust. They started their lives together, and that shared history, that's the master key to unlocking all their secrets.
So why are these cosmic families so perfect for scientists? Why call them laboratories? Well, it's all about controlling the variables, you know? First, they're co-evil. That's a fancy way of saying they all have the same age. And since they all came from the same well-mixed cloud, they're also chemically homogeneous. Now, this is the really crucial part. It means every single star in that cluster started with the exact same chemical DNA. Plus, since they're all grouped together, it's way easier to measure things like their distance and age accurately.
Okay, so we've got our perfect stellar laboratory. Now we need our forensic tools. And for a star detective, the number one tool in the kit is a way to analyze the light itself. It's a technique called spectroscopy. And really, this is the fundamental rule of stellar astronomy. We can't send a probe to a star thousands of light years away, but we don't have to. For billions of years, that star has been sending a constant stream of evidence our way, traveling across empty space at the speed of light. All we have to do is catch it and read what it says.
So how does this actually work? It's pretty straightforward, really. First, you need a powerful telescope, something like the 2.7-meter Harlan J. Smith telescope, which acts like a giant light bucket, scooping up all that faint starlight. Then, you feed that light into an instrument called a spectrograph. Think of it like a super high-tech prism that splits the starlight into a really, really detailed rainbow. And finally, scientists comb through that rainbow looking for tiny dark lines. Those are the clues.
And those dark lines are everything. See, as light travels out from the star's core and through its atmosphere, all the different chemical elements in that atmosphere absorb light, but only at very specific wavelengths. Every single element has its own unique pattern, creating what's essentially a chemical barcode, or a fingerprint, stamped right onto the starlight.
So by reading this unique chemical fingerprint, astronomers can figure out exactly what a star is made of, all without ever leaving Earth. Let's take a closer look at how they turn that barcode into actual, precise data. I mean, it's one thing to say there's a barcode there, but how do you actually quantify that? How do you get from just seeing a dark line in a rainbow to a hard number that tells you exactly how much of an element is in that star?
Well, the answer is a measurement they call equivalent width. It's basically a way of measuring the total strength of one of those dark absorption lines. The stronger and broader the line, the more light was absorbed. And that tells you there's a greater amount of that specific element in the star's atmosphere. It's how you go from just spotting an element to measuring exactly how much of it there is.
But this analysis is unbelievably sensitive. It requires incredible precision. Look at this table. The term FeH is just comparing the star's iron content to our sun. If your estimate for the star's temperature is off by just 100 Kelvin, which is not much at all, it can throw your final iron measurement off by almost 10%. It's this painstaking process where every single detail has to be absolutely perfect.
Okay, so let's take all these forensic tools and apply them to a real-world case. Our target is an open cluster named Messier 93, sometimes called the Critter Cluster. It's about 3,400 light years away in the constellation Puppis, and this cosmic family is about 300 million years old. Let's see what the detectives uncovered. The very first major clue was the cluster's overall metallicity. The analysis came back with this number, an Fe/H value of -0.17. So what does that mean in plain English? It means the stars in Messier 93 have about 68% of the iron that our sun has. They're a little less metal-rich,
And that is the first big piece of their unique chemical identity.
And this image, wow, this just shows the whole idea of chemically homogeneous perfectly. All those little black crosses are just random stars in the sky, and you can see their sodium levels are all over the place. But look at the red squares. Those are the stars from Messier 93. See how they're all packed together in a tight little group? That's their shared family chemistry, a dead giveaway that they all came from the same place.
But the analysis found something else, too, a specific little flourish in Messier 93's chemical fingerprint. Turns out, it's enriched in certain heavy elements, like cerium and lanthanum. These elements get created inside aging stars through something called the S process. So, this gives us a clue about the specific kind of chemical environment this cluster was born in millions of years ago.
So we've got a super detailed chemical fingerprint for the Messier 93 family. Why does this matter? Well, because this unique fingerprint isn't just a description, it's a tag. And this idea of a chemical tag is one of the most exciting concepts in all of modern astronomy. It's a concept called chemical tagging. You see, over billions of years, open clusters like Messier 93 will eventually drift apart. Its stars will get scattered all across the galaxy. But here's the thing. They will never lose that unique chemical signature they were born with. So if we can precisely measure a star's fingerprint, we can potentially trace it all the way back to its long-lost family, and we can start to reconstruct the galaxy's history, one star at a time. Now, as the researchers themselves point out, this whole incredible idea, this whole chemical tagging concept, it hinges on one single thing. Different clusters have to have different chemical fingerprints. If every cluster was exactly the same, the tags would be useless, right? And that's exactly why finding M93's unique signature is so important. It proves that these measurable differences really do exist.
And that is the ultimate goal of all this detective work. It's basically a form of cosmic genealogy. By finding one star's unique chemical signature, we can search through these massive galactic databases for a match, identifying its siblings that were scattered to the cosmic winds billions of years ago. We can literally rebuild the family tree of our entire galaxy.
Which leaves us with one last really tantalizing thought. Our own sun, it was almost certainly born in an open cluster, just like Messier 93, a cluster that broke apart and scattered a long, long time ago. So, if we can perfect the science of chemical tagging, could we one day scan the heavens and actually find the long-lost brothers and sisters of our very own star?